Alright, so I'm going to do problem 69 of chapter 10, which is a red problem. So they give you a diagram which is really hard to draw, but it's a cylinder within a small cylinder within a bigger cylinder, and so we're going to find the moment of inertia of the combined cylinders together, and to do that you have to find the moment of inertia of the small cylinder and the big cylinder and then add them together. Now the moment of inertia of a cylinder or a disc to go to MA, but it's with torques. So the torque created by the tension is the torque itself times the radius. So if you do some algebra, do some rearranging, this is what you get. The frictional torque is equal to the force of the rotational force of the tension, and then I alpha minus I alpha. And so that's the torque of the sum, so we'll just keep that in mind. We'll use it later. Now, this is the free body diagram of the hanging mass with tension up and then mg down. If we sum the forces in this free body diagram, this is the mass hanging off of the two cylinders. We'll get tension minus mg equals ma. And if we do some algebra and do some rearranging, we'll get tension equals mg plus ma. Okay, m. Alright, so we'll get that. Oh, this is negative. Alright, and then now we're going to have to use a kinematic to plug stuff in, and then or to find the acceleration, and then later we can plug that into, turn it into angular acceleration, plug it in here, and then find the frictional torque. So the kinematic is y equals v initial t plus 1/2 at squared. And v initial, we're applying this to our hanging mass. So v initial is 0, so that goes away. And then we'll just go ahead and solve for a, which is y over 2y over t squared. Now, with the equation a equals r alpha. Wait, no. A equals r alpha. Alpha equals ar. Alpha equals ar. You can find out that if we have the linear acceleration, if we just put an r on the bottom, this becomes angular acceleration. So now we have the angular acceleration, we have what tension is, and then we have what we need to plug into, we have our moment of inertia, and then we have all these three things we would plug in to what we found for rotational torque. So after plugging everything in, you plug in this for alpha, angular acceleration, and then you plug in this for tension, and you plug in this for moment of inertia. your final answer will be, that says frictional torque, will be T, mg minus 2y over t squared times r minus 5/8 mr squared times 2y over rt squared. Now that's kind of messy because that's not my final answer. I'm going to have to simplify it. So our final answer is frictional torque equals r times m times g minus 2y over t squared minus 5/4 my over t squared. And that is the torque that is acting opposite of the torque created by tension.